Great. So today's outline, first I'm going to start by going through some background. And so this is very much inspired by the fact that I am TAing this quarter. And so I'm TAing for one of Will's classes, his undergrad thermo class. And so in that class, in defects in batteries, we very often start with some sort of fuel cell and take that fuel cell, close off the ends. So you start having, varying pressures of oxygen in a solid oxide fuel cell. And then by closing off those ends, you're basically modeling what kind of happens in a battery. And so I'm going to go through a very similar paper that uses the same type of, ideology. And so I'll start by giving you some background, kind of set up a one-dimensional fuel cell problem and remind you of the basic equations from classes or introduce them to you if maybe you haven't taken those classes yet. Next, I'll set up the more conceptual picture. So like what's going where do ions go? Where do electrons go? Where do neutral species go? And what we're assuming. And then basically I'll do the thing that is the important part for my work, which is extrapolating to the batteries and what implications the results of understanding what's going on in a fuel cell have for batteries. And then finally, we'll talk a little bit about non-steady state. And I have this picture here is because I tried to basically replicate the model in this paper that I have cited here from UHN. Oh, no. Come on. We're doing so well. Cool. From UHN's paper at UPenn. It's a modeling-based paper about, transport bottlenecks in solid electrolytes, so for solid oxide fuel cells. And basically, my computer's already having a tough time with that. And if we consider, non-steady state conditions, that'll be tough. My fan is already on. Oh my goodness. Hold on one second. All right, hopefully this doesn't continue to happen. Okay, so let's get into it. So first, as I promised, we'll do a little bit of background on fuel cells. So if we remember from classes, fuel cells are essentially some sort of, in this case, a solid oxide fuel cell. You have some sort of membrane, and that membrane is going to be only permeable to ions. So in this case, we're doing oxygen anions, O2 minus, which travel very often by oxygen vacancies in the membrane. I'm saying the membrane here is YSC, which stands for yttria stabilized zirconia. Stabilized just means it's doped. And so then you have two electrodes, and they're gaseous electrodes, one side being, totally oxygen electrode, the other side a hydrogen electrode. So it's got this very low partial pressure of oxygen. So high pressure oxygen, low pressure oxygen. And if I select the right one, and continue with my script. We know from our defects classes, from our, thermodynamics classes that the chemical potential of a given gas is going to be it will scale with very generally RT, gas constant, absolute temperature, times the natural log of the partial pressure of some gas. So I'll just leave it as gas for now over some reference pressure. And so if we take that into account, that is the relationship we expect, then we know that the chemical potential in the oxygen electrode is going to be greater than the chemical potential of oxygen in the hydrogen electrode. Okay, so the thing is, now we can say, if we're trying to think about what's happening in terms of the chemical potential of the neutral species in our fuel cell, so oxygen, for example, we know, again, that the chemical potential is lower on this side, being the hydrogen side, and it's going to be higher on the oxygen side. But what does it look like in between? So to kind of understand that, we can set up a few of our, fundamental equations. So oh my gosh, this is gonna bother me. Hold on one second. I'm going to flip this around. Hopefully that will be better. Okay, and so we can look at some of our fundamental equations. So for one, the creation and annihilation of our oxygen vacancies, so O2 minus, is going to essentially equilibrate with the generation of oxygen gas and electrons, or going in the reverse direction. depending on if you're charging or discharging, if you're in electrolyzer mode or solid oxide fuel cell mode. Within the electrolyte, we can have electrons and holes being created or annihilated. We know that any sort of reaction that can equilibrate, that the sum stoichiometric coefficients, mu sub I, times the electrochemical potential of the species is going to be equal to 0 for, again, anything that can equilibrate. And then finally, we know, for in general current of any sort of species, so whether it's ionic or electronic, is going to be equal to the negative of the conductivity of that species, so ionic or electronic conductivity, the charge on that species, elementary charge E, and then the gradient in chemical potential or electrochemical potential of that species. And so just to review solid oxide fuel cells versus electrolyzers, you can see down here, a fuel cell is kind of the same thing as if you imagine you're discharging a battery. An electrolyzer cell is kind of the same thing as you're charging the battery. So what that looks like is that in discharge mode, basically the electrons are going to naturally want to go this way around the circuit. And so you're basically going to be consuming the oxygen, creating these O2 minus that jump through the YSZ membrane, which combine with the hydrogen here that forms water, generates electrons. I think I need a 2 in this equation, and then the electrolyzer is literally just those reactions in reverse. And so as you would expect, the oxygen anion is going to go the opposite way in the electrolyzer. So with that, let's jump ahead. And now that we kind of understand where things are going in the fuel cell, whether you're in fuel cell, discharge mode, or electrolyzer charge mode, let's think about what's actually going on with our electrons. So first, the conceptual picture of the electrons. One of the things that's very important, which we kind of know exists, but very often might forget is very important, is that through your membrane, whether it's a liquid electrolyte, solid electrolyte, or YSC in this case, probably more so with the solid electrolytes and YSC membranes in a solid oxide fuel cell, there's going to be some leakage of electronic current through the solid electrolyte. When we set up these problems theoretically, we often say, okay, it's perfectly like ionically conducting, but not so perfectly, it shouldn't conduct any electrons whatsoever. But it does in reality. And so what we have to think about here is T sub I, which is going to be commonly known as the transference number. And then for the it's basically going to be the ratio of the ionic to the total conductivity, so ionic and electronic. And when I say electronic conductivity, it's important to note that electronic conductivity can come from two sources. It can come from the conductivity of electrons in an electrolyte and the conductivity of holes. So depending on which one is your majority carrier at a given location, spatial location in your electrolyte, one or the other might be contributing more strongly to the overall electronic conductivity in your membrane. And so one thing to note here is that very often for a good electrolyte, you assume this is essentially 1. So it's close to 1, but for this case, we're going to say it's not equal to 1. So it's very important that it's not equal to 1. Additionally, we know from our Nernst equation that potential of a cell is going to be roughly proportional to the natural log of the partial pressure in the cathode over the partial pressure of the oxygen in the anode. And that is in itself proportional to the change in electrochemical potential of electrons, which is the more fundamental definition of voltage in the anode minus that in the cathode. And so you'll see here on the left, something that I likely spent too much time on, but our fun mnemonic devices, if you ever find yourself forgetting, I do constantly and have to spend at least like an extra 30 seconds going through this in my head to make sure I'm right. But we have the two mnemonic devices, which is Leo says GER. So if you lose an electron, you're oxidizing. If you're gaining an electron, you're reducing. And then red cat and ox. So your cathode is where something's being reduced and the anode is where something is being oxidized. And so if we take a look in the solid oxide fuel cell and solid oxide electrolyzer cell, we can analyze what our potential looks like. So for the case of the solid oxide fuel cell, our cathode is the is the oxygen electrode, and our anode is the hydrogen electrode. And so basically the cathode is going to have a higher, or the oxygen electrode is going to have a higher partial pressure than the of O2 than the hydrogen electrode. And so in this case, you find that the potential is greater than 0, opposite in the case in the solid oxide electrolyzer cell. And so in both cases, we find that the chemical potential of the hydrogen electrode is going to be greater than that in the electrochemical potential of electrons in the hydrogen electrode is going to be greater than that in the oxygen electrode. And from this, we know that the electrons are likely going to want to leak from the hydrogen electrode to the oxygen electrode. So we basically figured out that we can edit our diagrams from above and add in a little reference to electrons and which way they're always going to be want to be leaking through solid electrolyte. And so sometimes it's concurrent with the ionic current and sometimes it's anti-parallel. All right, so next, we actually want to start to plan out or understand what the electrochemical potential profiles of electrons and ions and even the neutral species look like throughout the solid electrolyte that we're considering. So what do these look like? First, let's take a simpler case at OCV. So there's no current, we don't have to think really about the direction of current. So if we look at our cell, OCV is essentially, we're defining that there is no net current. So there's no total current. J total is 0. And the J total, or the total current, which is 0 in this case, is going to be the sum of the ionic current, so O2 minus, and the electronic current, J sub EL. And remember, the electronic current is going to be both the current of the holes and the electrons. So if I say E sub L or sub EL, that means electronic. If it's an E with a little minus sign, that's for an electron. Additionally, we know that we've already kind of covered that roughly current is going to, of any species, is going to be equal to the conductivity of that species divided by the charge on that species times the, or divided by the elementary charge, and then the gradient in the electrochemical potential of that species. So I'm making it one-dimensional, the mu tilde dx. All right, so let's think. Let's go through this slowly and think about what we can expect for these profiles. So first, I'm setting it up here. We're going to have 3 different plots. First, we're going to start over here with the electrons. So I'm going to set up a very, easy, nice to conceptualize situation. So let's just say that our electronic conductivity to begin with is constant. So this doesn't change throughout. You just have constant electronic conductivity. And we'll analyze in a bit what happens when that's not the case. As we already talked about, the chemical potential of electrons in the hydrogen electrode, or the electrochemical potential of the electrons in the hydrogen electrode, is greater than that in the oxygen electrode, and that comes from the partial pressures. And then finally, I'm just going to start with this, what's it called? Formalism that the electronic current is going to be in negative. So we said before electronic current is going from left to right. I'm going to say that the right to left in the discharge case for, the O2 minus is going to be a positive current. So we have the chemical, or the current of the electrons is going to be less than 0. And so continuing on with that, if we start to look at our plot, we say, okay, for our electronic conductivity, if we plot it out, let's just say that's going to be some sort of straight line. And then for our chemical potential profile, we know it's going to start at some higher value up here and go to some lower value down here. So we don't exactly know what that looks like yet in the middle, but we know that it's just in general decreasing. And that again comes from our knowledge of the partial pressures. All right, so next, we go ahead and look at our ionic conductivity. And again, to make things simple, let's imagine a constant ionic conductivity. And so drawing that out for you, we're going to say it's just constant throughout. And so just so you know, the x-axis is going to be from left to right, from the hydrogen electrode to the oxygen electrode. And you'll notice here that I drew the ionic conductivity is higher than the electronic conductivity. And that just comes from, it won't matter for too much for the solution. It does change things a bit, but we want to assume that the ionic conductivity is much greater than the electronic conductivity because otherwise you're not going to want to actually use that as your electrolyte. Okay, so continuing on, we can basically say that for our studies, or for our open circuit voltage, we know that the ionic current plus the electronic current, which is the total current, is equal to 0. So that means the two are equal and opposite. So this is equal to negative J of the electronic current, and thereby the ionic current, O2 minus, is going to be greater than 0. So we have some sort of, positive slope. And as I said before, the electronic conductivity should be much less than the ionic conductivity. So if we start to look at the electrochemical potential, or at least their profiles, then we'll see that for our relationship between current, as we have up here, current, conductivity, and the gradient in electrochemical potential, if we kind of solve this equation and this equation together, we will end up seeing that the gradient in mu for the or for electrochemical potential in the ionic case is going to essentially equal 2 times the 2 times the electronic conductivity divided by the ionic conductivity times the gradient and the electrochemical potential of the electrons. So, negative, this should be negative. And so because we know that the electronic conductivity is much smaller than the ionic conductivity, this is going to be a smaller number. So we'll end up with some sort of positive gradient in the electrochemical potential of ions. And so we know that it's going to be essentially like, I'm going to draw it as a small arrow because it has a slightly smaller slope in this case. And then finally, let's get back to our chemical potential of neutral oxygen. And we kind of already know that it's going to be a positive number because we decided way back here that that we are, or way back here, that our chemical potential of a gas is going to be roughly proportional to the partial pressure of oxygen. And so in the hydrogen electrode, it's going to be lower than in the oxygen electrode. And so back here, we know that we're essentially going to have a positive slope, but just again, coming full circle, checking our work here, we know that the chemical potential of oxygen, based on the fact that this is a reaction that can equilibrate, is going to equal 2 times the electrochemical potential of the oxygen anion minus 4 times the electrochemical potential of the electron. And this comes from the fact that for reactions that can equilibrate, the sum of the stoichiometric coefficients times their electrochemical potentials for each species involved in a given reaction is equal to 0. And one important thing to say here is you'll notice that I've taken off the little tilde here, and that's just to say that because oxygen is a neutral species, its chemical potential is equal to its electrochemical potential. Is there a question? Okay, cool. Maybe just check if you're unmuted or muted. Cool. So from this relationship that we have here, we can continue on and say that if we take the gradients of these, we'll have the same relationship. So d mu O2 minus dx minus 4 d the electrons dx. So we've already decided that the gradient in electrochemical potential of the ions is greater than 0. We have that right here, it's greater than 0. And for the electrons, it's less than 0. And so one thing that we essentially end up finding is that because, the magnitude of this is smaller than this, even though this is positive, this is negative. And so overall, if you add those up with the opposite signs included here, the chemical potential profile of neutral oxygen in the electrolyte is going to be greater than 0, which we already found, and it's going to be bigger in magnitude than both of these. So it's going to be big arrow. Okay, we've got OCV down. This all checks out. Everything makes sense here. let's continue on and consider what happens at steady state instead. One thing that may be counterintuitive at this point is, why we care so much about the chemical potential of oxygen in the solid electrolyte. If you think about Y as Z at this point, it's not really supposed to have oxygen in it, right? And so as a teaser, it's important that we make sure that the chemical potential of oxygen, or whatever neutral species you're considering, it could be lithium, for example, solid lithium, we want to make sure that that is going to be, it's not going to be favorable for oxygen to exist in the solid electrolyte. You want it to stay ionic and you want it to stay as electrons, and you don't want the prevailing species to be, an oxygen gas bubble or a solid lithium. So continuing on, we're going to start to look at steady state instead. So the ionic or electronic current is going to be constant at steady state. So both are constant. They're not necessarily equal and opposite as we had in the OCB case. And so for the solid oxide fuel cell, we have that the electronic current going in and out is going to be equal, and the ionic current going in and out is going to be equal. I think I have the arrows reversed here, but it's the same idea. And then in the electrolyzer cell, they're going to be going in the same direction, whether that's left to right or right to left, doesn't matter. They're just going in the same direction, and they are going to be constant. So whatever is going in is coming out. And then next, just as a reminder, we know that current, so J of a given species, is dependent on the conductivity and the gradient of that species, the electrochemical potential gradient in that species. So let's go through the same process that we just went through. So we already know we're going to keep some things the same. So we're still going to say that we have some sort of constant electronic and ionic conductivity. So I filled those out. That doesn't change anything about the electrochemical potential of electrons. It should basically be the same. It doesn't really change anything about the chemical potential of neutral oxygen. That should essentially be the same. The one thing that might change, however, is before we did find our potential profile for the ions dependent upon that current relationship. So let's go through that again and check if it's still the same or if something has changed. So the electronic current, as we said before, because we're in steady state, is going to be constant. And so because the, as I have up here, the current depending on the conductivity of a given species and the gradient in the electrochemical potential, then we find that if these two things are constant, then this also has to be constant, which means for us that we end up with a linear slope between those two pinned points. So just filling that in here, we can connect these by a straight line. Okay, that's one situation solved. Let's look at the ions. So again, we're saying constant ionic conductivity. And in this case, because ionic and electronic conductivity are not equal and opposite, we can't necessarily say that we're going to know exactly what it is, but we'll say that this is going to be constant. For the solid oxide fuel cell, we already mentioned that we want our current to be greater than 0, and this is going to be the discharge case, and then it's going to be less than 0 in the charge case, which is the electrolyzer cell. So this means, again, same as with the electrons, we're going to have some sort of constant gradient in the electrochemical potential of the ions in the O2 minus. But we have to carefully think about the sign, because in this case, we have current either being positive or negative. In this case, we knew it was going to be negative because our current is going to be constant and negative, but it's either constant or positive or constant and negative, depending on if you're dealing with a fuel cell or a solid oxide electrolyzer cell. So, trying to plot those out specifically for you here, we can say that for the fuel cell, which I'm representing with this undashed line, we know that the current has to be positive and thereby the gradient will be positive. And then the opposite goes for the electrolyzer cell. It should be negative and constant. So we have these constant profiles. All right, returning to our chemical potential of oxygen. Again, we already know it's pinned by these 2 points. It's always going to be pinned by the 2 points here and here. But what does that actually mean for the profile in between? And so because we already know the profile, we know that the gradient is going to be greater than 0. And again, we already have this set up for our overall reaction. This is the sum of the stoichiometric coefficients times those electrochemical potentials and the gradients that result. And so if we take a look at the signs here, we have that the chemical potential, or the gradient that we know is greater than 0. And we know that for the electrons, the electrochemical potential of the electrons is going to be negative. So this term is less than 0, but when multiplied by this negative becomes positive. So this kind of already checks out with this. But we know that this gradient changes. We know that for the fuel cell mode, it's greater than 0. And for the electrolyzer cell mode, it's less than 0. So just, nominally, this already kind of indicates that the magnitude here is going to be smaller, and therefore the dominating factor is the electrochemical potential of electrons and how that actually influences the chemical potential of the neutral species oxygen throughout the solid electrolyte. We can kind of go back and say, okay, if we're just adding these two things up, we know both of these are going to be some sort of combination of straight lines. So as you can imagine, the connection between these two is also going to be a straight line. Okay, so now we know steady state mode in both fuel cell and electrolyzer cell modes in a very simple constant conductivities throughout situation. Now let's get a little bit more real here. And let's talk about maybe potential situations in which that may not be the case. So the first one I can think of, and that the paper thinks of, is that, well, it's probably a misnomer to say that I can think of it. This was not immediately apparent to me, but electronic bottlenecks naturally arise within the solid electrolyte. When I say electronic bottlenecks, it's just a local place where the conductivity of electrons is lower. And this can happen just because you actually are changing the majority carrier of that electronic conductivity. I mentioned before, when we talk about electronic conductivity, sigma EL, that's going to be comprised of the electrons' conductivity and the hole's conductivity. And so let's take a second to look at how charge carriers are interacting in this system. So first, in terms of charge neutrality, we can kind of assume that locally. It may not be true on every length scale, but at least throughout the solid electrolyte, there should be some sort of charge neutrality, meaning that, for every hole that's generated, there should be a complementary electron, or for every oxygen vacancy that exists, there should be, 2 complementary electrons to balance the charge, because we're going to have a +2 charge here. Additionally, the law of mass action kind of tells us the relationship between generating these oxygen vacancies into oxygen. And so during charge and discharge, the oxidation and reduction of oxygen reaction can equilibrate, as we said. And so the concentration of holes and electrons and oxygen vacancies will all depend on the partial pressure of oxygen. And so finally, because the electrolyte is pinned between a high and low potential, or high and low PO2 electrodes, it's possible that there's actually going to be a crossover in what's dominating our electronic conductivity, whether it's holes or electrons. And so what that kind of looks like is you have on the x-axis the different, either the chemical potential of oxygen, which is related to the log of PO2, natural log of PO2, and some sort of conductivity. So the total electronic conductivity, depending on what potentials we're actually going through as we're charging and discharging a given cell, dependent on the partial pressures of oxygen in each of the electrodes, could actually reach a place where there's a local minimum. And so this kind of data that I'm showing here actually comes from things that have been measured for YSD electrolytes. And so this is a phenomenon that does indeed occur. And so again, as I said, depending on your electrodes and your applied potential, you may or may not intersect a crossover. But there is a situation in which a solid oxide fuel cell and electrolyzer cell will actually go through this crossover. So this can be thought of as kind of a local minimum in electronic conductivity. These are the defect reactions that go into that. But let's take a second to look at what happens when we vary the electronic conductivity, as I said. So going back to our situations from before, basically we have the same exact situation as we had ionically. I'm still saying we have a steady state, constant ionic conductivity, constant ionic current, we should expect the same things out of the electrochemical potential profile. The thing that changes is our electronic situation. So first, we've already said there's some sort of local minimum in the electronic conductivity throughout the system. Say we are actually going through that potential sweep that does intersect that local minimum in electronic conductivity. Additionally, we are saying this is constant. We're still at steady state because my computer can't take it. And then finally, let's take a second to try to reason out in our heads what would happen to the gradient in electrochemical potential of the electrons. So again, we know that our current is going to equal negative sigma EZ gradient in chemical potential of a given species. So if we have a dip in the conductivity or the electronic conductivity, then we will see that there is going to be some sort of, for a constant current, some sort of jump in the electrochemical potential gradient. Now, because we have the current as being less than 0, you can also think of it as a dip. So it's an increase in magnitude, but it's negative. So it stays negative here. And if I missed something in the chat, please feel free to chime in and interrupt. I don't mind, because I will not look at it. The local dip in the gradient of the electrochemical potential of the electrons is going to be associated with a local jump in the, in the chemical potential of electronic species. It's going to be associated with a local jump in the gradient of the electrochemical potential of the electrons. And so this is the situation as we had it before. So this is just, our constant electronic conductivity. And so then below that, we can now say, all right, if we have some sort of dip, and that dip I will draw maybe rather poorly, but some sort of dip, I want it to be centered, in electronic conductivity. Again, we're going to say that there is some sort of very large increase in the negative gradient of the electrons. So if we're still connecting everything, that essentially kind of takes on this shape. Cool. And we already have the profile here. So let's take a second to think about what the profile looks like in terms of the neutral species, in terms of oxygen. So again, we have already figured out what's kind of going on with the gradients based on the law of mass action, or based on some of the ability to equilibrate here. And so now we have, again, we're kind of considering we have the same gradient profile in the oxygen ions, but the thing that's changing here is the gradient profile in the electrochemical potential of the electrons. And so we can say that if there is going to be some sort of local jump, oops, it's a local jump, or I guess we can kind of look at the chemical potential instead. So if we look at the chemical potential, there's a local dip. If we're looking at absolute, or we're actually looking at the values of things, there's a local dip in the electrochemical potential of the electrons. Then we're going to say, okay, there should also be a concurrent local jump in the electrochemical potential of the, or the chemical potential of the oxygen, which just comes out of looking at this equation. If this goes down, this has to go up because of the negative sign. So what that looks like is essentially this equal and opposite, maybe to a greater magnitude, oxygen chemical potential profile. The best I can do on the spot. I promise I have a very beautiful version where I just erased everything for this presentation. Okay, so now we know what happens when we have some sort of minimum in the conductivity of electrons. And the reason why it gets interesting now is because you have to remember that essentially at these points, this is corresponding to neutral oxygen existing over here and neutral oxygen existing over here. And so the idea is if you've got more of a region within your solid electrolyte that's actually very close to these potential barriers. So if there's any more anomalies that might occur, there's potential that your neutral species chemical potential could dip or could jump or dip to a point that you're starting to produce this neutral oxygen within the solid electrolyte or voids. And these are actually things that are observed. So let's take it that step further and add that anomaly and see if that will produce what we expect, which might be a jump in chemical potential of oxygen, and thereby some sort of degradation reaction in our solid electrolyte that we do not want just because of a transport property. So let's consider that ionic bottleneck. That's another place that we can kind of add in an anomaly. And when I say ionic bottleneck, one thing that you can think of is like a grain boundary that's like perpendicular to the flow of ions. And that should be a sufficient dip in ionic conductivity to consider. So again, we kind of have the same deal for electrons. And this is a situation that we just went through. I just brought it down here so everyone could see it. So the electronic case, everything's the same. Now let's vary the ionic case. So if we think about what happens, again, maybe at some sort of, excuse me, at some sort of local dip in the ionic conductivity. So local dip in the ionic conductivity. For a solid oxide fuel cell, that would mean that our chemical or electrochemical potential gradient of the ion is going to be a greater than 0. We already have this. And for the electrolyzer cell, the gradient is going to be less than 0. We already know this from our previous cases, but we have to think about the local dip in ionic conductivity has to be made up for by a jump or a dip in the electrochemical potential of the ionic conductivity. So depending on the direction you're flowing, you're going to have these different signs of your chemical potential profile or electrochemical potential profile, and therefore different signs on your current. And so a dip is going to lead to either a sharp jump here or a sharp dip here. And so I'm not going to try to draw that for you on the spot. I'm smarter than that. But it's essentially going to look like this. For this localized dip in the ionic conductivity, for a fuel cell, you see this sharp increase, and this is going to be for our electrolyzer cell. It's again a sharp increase, but in the negative direction because it's going to be a negative potential profile. And just zooming in on what that looks like, I drew it rather small. The magnitude here, an important note, the magnitude of the sharp jump or the sharp decrease depends on the size of the dip in the ionic conductivity. So if you have like a really low ionic conductivity grain boundary, that's going to be very important to know about if that jump across that parallel grain boundary is important. Okay, almost done. Now we're going to look at the neutral oxygen case. This is the one that's kind of exciting now. So a local dip or jump in our electrochemical potential of O2 minus is going to lead to a local dip or jump. And these are relatively speaking. So a dip in one is a dip in the other because they have the same signs, or jump in the chemical potential profile of O2, so the neutral oxygen species. And again, I'm not going to try to draw it for you on the spot. Instead, let's just take a look. So if we look at our fuel cell case, we say that, okay, for the fuel cell case, there should be a jump here. So it should look like this. And if we add that into our system, it essentially looks like this jump here. And then if we look at our electrolyzer case, same thing, but instead we have a dip. And again, in order to satisfy the boundary conditions of the partial pressures of oxygen on either side, we see that there has to be a dip and then it comes back. And so now we've entered this red zone here. This red zone is basically anything up here is going to be an issue, and anything down here is going to be an issue. Up here, that means that you're producing oxygen. You can make an oxygen bubble within your solid electrolyte. And down here, it means that maybe you're creating a void. And again, these are all anomalies in your YSC that you do not want because basically it's some sort of transport bottleneck that is causing some sort of energy to go into putting things where you don't want them. Okay, so we've kind of shown that it's important to know what kind of anomalies exist in your membranes and your electrolytes and anything. And one thing that I will note is, say that you had like a grain boundary closer to the middle, that would probably not push you over the edge. You know, it might jump up a little bit and that won't be so much of an issue. Over here, if you have this, you might think that, oh, like if I have the fuel cell, then it would dip down here, but that's not actually the case. If you have the fuel cell and you had some sort of anomaly over here, it would jump up here and then continue on with the regular profile. For the electrolyzer cell, again, you'd have some sort of jump and then it would kind of stabilize back. And so you'd have this kind of little dip that occurs. And so the work I've been doing recently is actually replicating the model parameters based on YSD to create this. And again, my computer has not been happy about it, but I am working through it slowly. So one of the things that I think is most important and very interesting for a lot of us here is that you have oxygen bubbles or voids forming on charge. So in the solid electrolyzer cell, solid oxide electrolyzer cell mode, but no degradation on the discharge. And that's just because of the shape of these profiles and because of the shape of the electrochemical potential profile of the electrons and everything that's causing it. And so that's why this bottleneck in electronic conductivity is actually incredibly important to the neutral oxygen, even if it seems a little bit counterintuitive to begin with. And so what we get is direction-dependent degradation. And we see this a lot in lithium-ion batteries. I know in my cells, one way it's, if you just charge, it's going to have much different impacts on than our discharge. You have not only different reaction kinetics, but sometimes different transport kinetics. And I know I put lovely fireworks here, but maybe this is not so great because it might look like contribute to capacity fade as it does in my cells. So now we're getting to the extrapolation to batteries. And I know I only have 8 minutes left, but I have like 5 minutes of content, so it should be fine. And so in terms of solid state batteries, which is the thing I'm concerned about, this could explain potentially why there's lithium plating within the solid electrolyte. And so this is one of the theories that I think is mulling around the anode solid state battery group. I'm doing the positive electrode, but doesn't mean I'm not interested. And so that could be one possible explanation for lithium plating inside the solid electrolyte. There are a number of other possible reasons, but this is one thing to consider. Additionally, if we think about battery interfaces, so this is in any lithium ion battery, you have a CEI, which is a cathode electrolyte interface, or an SEI, which is a solid electrolyte interface. And basically, you could have directionally dependent formation of these interfaces, depending on if there's some sort of degradation occurring at either electrode, meaning that there's some overshoot in the chemical potential profile of lithium. And then finally, you can actually kind of take this and instead of looking at some sort of electrolyte, so it's a liquid electrolyte in lithium ion battery, solid electrolyte in like LLZO or LPS for me in the solid state battery situation, you can also apply the same exact transport model to your actual electrode. And so, you know, if you have some sort of ionic or electronic bottleneck in your electrode, which is the case in my electrodes, you can also have different types of degradation happening within your cathode materials. And we have, or anode materials, and we have subgroups dedicated to both electrodes, which hopefully you will find interesting. And so the thing is, we are missing one key parameter. And that parameter, I spent a while on that key, but I spent even more time on time. And the thing is, time is important because we're not in a system where you have a constant partial pressure of oxygen, constant partial pressure of oxygen in the hydrogen electrode. Instead, you have these varying chemical potentials of lithium in each, and you have different amounts of applied current, applied voltage. And so after, you know, actually being able to replicate the work done in this original paper, I'm hoping to extrapolate it to non-steady state systems. So again, we have this chemical potential profile of lithium, where this would be your negative electrode, this is your positive electrode being NMC, the thing I care about. And so if we look at what that looks like at non-steady state, well, now you've got this changing pinged electrochemical potential of lithium. And so how does the total current actually vary with potential also becomes very important. And it will change essentially what this profile looks like. You might move it left or right. And there is some work in the paper that I wasn't able to talk about that does show that the total current that you apply is actually going to change where this kind of this vertical asymptote kind of occurs. Not asymptote, but drop. You know, what happens if we have kind of an ohmic type of relationship between current and voltage, or a charge transfer limited reaction. And so all these will become very important when we start to allow things to not be at steady state. And again, maybe tough on my computer. So with that, I want to thank everyone. You might notice that I just literally copy and pasted this from my December talk. So I did not spend twice the amount of time on thanking you all, but thank you for listening. Would like to especially thank the solid state battery subgroup. But I also count Joe Long in that because he helps me constantly. I've talked to most of the people here about this paper, and they've spent at least the last 2 weeks talking about it. Special huge thanks to JJ and Stephen, who have been also mentoring me a lot, which takes a lot. I ask a lot of questions, and it's a good thing, I hope. Stephen in particular, who I've talked to several times past midnight about this paper just randomly. So I appreciate everyone's patience with me. I'm hoping it will benefit everyone in the group at some point. And therefore, thank you to everyone in the entire CHU group. This is me, right in the center, little face. Still bitter about the fact that when Justin and the Anno team and the first years pulled their friends, somebody said, if you had to guess who the PI was, it's somehow clearly not me. Still offended, not gonna get over that anytime soon. But yeah, I think that's everything. So thanks everybody.